Okay, let's get started here. It's 11 o'clock. So assignment number 3 is due on Friday, March 6th. Midterms coming up. It will be Tuesday, March 10th. Do note that since we met last, I have posted a formula sheet to the course website on the graded materials webpage that will correspond to the midterm exam. That formula sheet, you can use it as much as you want on the exam. Okay, are there any questions before we get started here? Then let's talk about these presentations. So if you have that handout that I posted regarding presentations, it would be handy to get it out now. Okay, so I developed this format for presentations after many years of doing a variety of different formats for presentations in classes, and I think this one actually works the best. The reason being is because the students have a lot of freedom to choose topics that they want to present, but also the students in the audience who are listening to the presentation benefit from a much more than, let's say, in a standard presentation format. Okay, so the purpose of these presentations is to give students an opportunity to explore topics in computational statistics that really interest you. And so what you will be doing is spending a few weeks, maybe a month, learning a topic on your own. And then present this topic to all of us for half a class period. Now, what especially makes this type of presentation different from maybe than what you've had in other courses is that in addition to your presentation, you have to actually construct your own homework assignment that will be given to the students. So that's why the students will be benefiting from it a lot more, that presentation, than just a standard format where you just speak and then the students can just forget everything that you just said, because they didn't really have to listen in the first place. So you have to actually construct a homework assignment. And I like this homework assignment to be small. You know, maybe like the equivalent of about 10 points on what you've seen in my previous 3 assignments. You can always run a homework assignment by me before, and I'd be happy to give you some input about, yeah, is it good enough? Is it the right length? Do you need more? So please feel free to talk to me about it. Now, also with this whole assignment, the students will actually be turning in the assignments. So I'll be giving you guys a few days to work on the assignment. You'll turn it in and I grade it. Tell me grade it. I want the presenter to give me a corresponding answer key. Now, let's actually take a look at the schedule about when these presentations will be given. So there's 8 students in this class, so it will take us 4 days to go through all the presentations. We'll start on April 16th, and eventually once we get closer to April 16th, what I will do is just put all your names in R and let R pick it for us in terms of the order. Unless there's particular students who really want to do the presentation first or second or whatever. If you want to get it out of the way at the beginning, please feel free to volunteer. Now, you see 2 days, day number 28 for our class and day number 31 for our class, where what we will actually have is just presentation discussions. You know, since the presenters will be given homework assignments, I want to give an opportunity for students to work on the homework assignment. And if they have questions, then they can ask the presenter on April 23rd or May 7th. And so they have an opportunity to ask questions before the students turn them in, then on the Friday of finals week. So they'll be due at noon. Now, obviously, I know, given that you are having to present, and it's towards the end of the semester, what this basically would mean is that every student's going to have to do 7 separate assignments. I decided that was a little bit too much, so I'll give you the option of picking 3 of the 7 assignments to actually hand in to me for a grade. Any questions about that? Okay. Let's see. So, obviously our final exam period then is one of these discussion periods. So, we'll, in terms of our regular formal tests, we'll just have the midterm. And I kind of think of then this presentation then as almost your final exam, you could say. This presentation will be worth 100 points. I think I said that last time. Okay. So let me get back to my notes here. So these presentations, so you can see as I was going through what I was going to say today, you can see I wrote a lot of notes on my sheet of paper here. So please make sure that you do take notes or go back and review the video if you want to take notes at that time. So the presentation, since it's a half a class period, they need to be between 30 and 35 minutes. If it's less than 30 minutes, points will be deducted. If it's more than 35 minutes, points will be deducted. So between 30 and 35 minutes. In terms of the specifics of the presentation, topics. Obviously, this is a computational statistics class, so it has to be a computational statistics topic. We will talk about shortly potential ideas for topics, but please feel free to develop your own topic. But any topic you choose, either if it's from my list that's on page 2 or if it's one that you came up with, you have to clear it with me first. Now, of course, that doesn't mean 1 week before your exam you're just starting to clear it with me. I'm sorry, let me reset. Don't wait until like 1 week before your presentation to clear a topic with me. Because what happens if I say no? You're not going to be very happy. So I would recommend that, basically, the week after the midterm, start thinking about topics. And then, you think of maybe spring break as essentially a deadline for, yes, you have zeroed in on a particular topic, you have a general idea of what to present, because obviously you only have 30, 35 minutes. You can't present everything probably about that particular topic. We'll see more about that as we look at page 2. So, you're going to have to focus. And that's why I want you to come to me and talk to me about the topic. Give me just a general, very general outline of what you're going to present. If you just said, I'm going to present a good one here. I'm going to present how to use MATLAB. If you only told me that, I would say to you, well, what about MATLAB? Tell me more about what you're going to do. Okay, so you have to have a general sense. I'm not asking for like a formal point-by-point outline, but I want a general sense of what you're going to do when you come talking about a topic. With these topics, essentially it's first come, first serve, I guess you could say, in terms of, if 2 people want to present something on MATLAB, well, whoever came to me first gets the topic. What I might do is say, okay, well, maybe you could talk to the other person about what they're going to present, and maybe you could do like a second part to how to use MATLAB. In terms of the presentation style, the key is that since students are going to be given an assignment, the presentation style should be in terms of a teaching format. Meaning, don't present it like you would at, like, let's say a conference. Let's say if you go to JSM, where you're presenting some research, and you might not necessarily really care a whole lot if the entire audience understands. What you're hoping is that maybe the people who know a little bit about this research problem, they understand. That's what you would do at JSM. Here, you need to make sure that all students in the course understand what you're presenting. So that's why it's in a teaching format. So one way is to use a similar style to what I use when I teach this particular class. I'll present some stuff, do an example, present some stuff, do another example. The key is, again, students need to be able to do your assignment. So if they can't do your assignment, then you will lose points on your presentation because it wasn't essentially done in the correct format. with respect to grading, like I said, there's going to be 100 points possible. And this is how I break up your grade. 40% for presentation quality itself. So essentially, it doesn't really have much to do about statistics, but it's evaluating your ability to present material. So, before you do a presentation here, you should practice it out loud. Practice it. So, for example, whenever I give a seminar or a presentation like at JSM, I usually will practice it out loud at least 5 times. At least that's what I've found for me. That's how long it takes before I feel as though, yes, I've got it down. I know I'm within the time limit. Everything's coming out smoothly. I have nice transitions between my different points. But sometimes I might do 10 or more times. In fact, that's what I did this summer when I had to give a presentation. I just couldn't get it done really well. I probably practiced about 12 or 14 times out loud. And I do want to emphasize out loud. Don't let's say if you create some PowerPoint slides and you go through the rehearse slides part of PowerPoint, you're just kind of saying to yourself in your head. Often what I have found when I've done it and what I've seen other students who have done that format, when they actually give it out loud for the first time, it just doesn't make sense. Or perhaps it's a lot longer than what it was when they were just kind of saying it to themselves. So make sure you do actually verbally say the stuff out loud. Was there a logical flow to the presentation? Does it make sense to talk about point A, then go to point B, then go to point C? Or maybe point C should have been first. That's what I'm looking for there. Were there transitions between items? Is there essentially a logical flow? So, for example, when I transitioned from bootstrap hypothesis testing to permutation tests, there was a nice little transition that I made between the two. I related the two before then solely focusing on permutation tests. I don't want to have topics disjoint. That's not a good way to give a presentation. Were the slides or other visual tools readable? So if you do slides, or you can use a Word, that would be fine with me if you just want to type it up that way like I do with my lecture notes. Were they readable? So let's say if you're doing a PowerPoint slide and you have a white background, should you use a yellow font? Probably not. Okay. Then 40% content. This is a statistical part, or the main statistical part. Was there a meaningful amount of items covered, or did you spend 30 minutes talking about how to calculate a sample mean in MATLAB? Well, I think you can do that in less than 30 minutes. Was everything actually correct? Then the last 20% of your grade is inside and outside of class learning tools that you provide. I would like all of you to provide handouts to students so that they have something that they can write on in terms of notes while you are presenting. The homework assignment itself, was it at an appropriate level for the students? Could they actually do it, given what you talked about and the resources that you gave? And also, did you give me an answer key? Was the answers correct? And since it's computational statistics, you might expect there might be some computer programs you're going to write. Well, I need to see those computer programs. You need to give them to me, either if they're in the answer key or if they are associated with your talk or your presentation, that all students need them.
As far as providing handouts, will we be able to send those to you ahead of time and have them posted on the
Yes.
website? Okay.
Yeah. But I do recommend that you bring paper handouts,
Okay.
but I do want to post them to the website too. Now, I've used this particular format now for 2 classes, and it was my Tools for Statisticians course that I taught the previous 2 springs. And so because of that, I have some examples or I have some good examples of how students have approached this. So I have examples from Amy and Trevor. Amy from 2013, Trevor from 2014, that you can view. Now, this is on the grading materials webpage. So I showed the handouts, I showed the homework assignment, I showed the actual video. Sorry, I failed to mention this too. Just like how I recorded everything here, we will be recording your presentation too. Once we get closer to the presentation time, I'll talk about exactly how we will do that. It's just simply using Camtasia Relay, if you're familiar with that. Do note that Amy actually had a whole class period presentation, so obviously it's a little bit different from us. She was able to get into a topic in more detail. The topic that she chose was how to use the ggplot2 package in R, and to be honest, that's kind of borderline if that would be a computational statistics topic for our class. You know, if you wanted to do something similar to that, I would consider it. Trevor, though, talked about Amazon EC2. Does anyone know what Amazon EC2 is? Okay. Basically, that's a way that you can use cloud computing. And so Amazon obviously has lots of computer resources available, and you can essentially log on to their computers. You can actually do it for free and run R on it, for example. And so he talked about essentially how to use their supercomputers to do stuff. And so there was a lot of non-statistic aspects to this, but definitely it's a computational statistics topic. Okay, are there any questions so far? Okay, so let's talk about potential topics. So originally, when so early last fall, I came up with I knew I wanted to do presentations in this class, and I was anticipating about 5, maybe 6 students in this class. You know, in the end, we ended up having originally 11, or maybe you might got up to 12 students at one point. And with 5 or 6 students, what I was going to have students do was basically take the entire semester as part of their presentation to learn a computer programming language other than R. Because it's not just R that's used by people, but it's, you know, there's a lot of other languages out there. And so what you can do for your presentation, and then there would have been obviously enough computer languages out there for 5 or 6 students. I started getting worried when we had 11 students. So I scratched that idea. But I think that, you know, a few of you in this class could simply take the time, learn one of these or other computer programming languages. If you already have a background in some of these computer programming languages, that's okay with me. I would anticipate through you constructing your presentation, you're still going to learn a lot more than what you knew before. So that will be okay with me. So you could present, for example, the basics of how to use a programming language called Julia, for example, which is a fairly new language that some people are using. There is a statistics core to that, but it's not just statisticians who use it. So present how to use this language to us. You know, how can a student, obtain the language and use it on their computer? Do a hello world program that you often see at the beginning of any kind of programming class. Maybe get a little bit into loops or if-then kinds of statements. Also, talk about the statistical capabilities of it. Are there maybe libraries that you can access that will make your life simpler with using a particular programming language? Again, you only have 30 or 35 minutes, so you're going to have to pick and choose. But at the very least, someone should be able to run a program in the language that you're talking about. You could also talk about an integrated development environment, IDE. In other words, what's a program editor that you can use? How can you maybe access a compiler if a compiler is needed? Okay. So there was, when I was preparing for today, I came across some few interesting links that you're going to see in kind of light blue. You can write them down if you want, but you can always obtain them from the video too. So let's talk about the next one here. There's, as you might expect, a variety of R packages available for for computational statistics. Obviously, we were talking about the boot package, for example. But what you could do is pick a particular package that interests you and present how to use it. So for example, there are a number of task views on CRAN's website, one on high performance computing, one on machine learning, and one on optimization, where there'll be a lot of stuff there that will be appropriate for one of our presentations. In particular, one that I have an interest in learning how to use that I don't know how to use right now is the RMPI package, and that is helpful for high performance computing that will allow you to do parallel processing. Now, I know we haven't talked about parallel processing yet, but I want to briefly mention what this RMPI does. Now, with parallel processing, basically what that means is you can think of it from this standpoint. This is a simplistic view. You're using multiple computers to do essentially a single set of calculations. And what RMPI does, it allows you to use these multiple computers in a lot better manner than what some of the standard R packages allow you to do. In particular, there are what are called nodes. We'll learn more about this once we talk about high performance computing. So let's say that there are 4 nodes in a supercomputer. Each of these nodes might contain an actual, let's say, computer processor. So maybe each of these nodes contains 3 processors. Okay. The standard methods in R to do parallel processing allows you to use these 3 processors all at once. What RMPI does allows you to go across nodes. So in other words, it will allow you to also use the processors here, the processors here, and processors here. I talked to some people at the Holland Computing Center here on campus, which controls the high performance computing, and they are not for sure how to do that in R. But I know of ways, I know this RMPI package is set up to do it. So part of your presentation then is you need to teach yourself how to do it and then present it to us so that we can do it. I think it would be very useful if someone figured that out. One could present how to use GPUs for statistical calculations. So, So GPUs are graphical processing units. So you're used to seeing like the Intel commercials for a CPU. And that's what controls most of your, like when we run R normally, that's the CPU is what's doing all the calculations for you. Now people are using also GPUs. What controls the graphics on your computer, they don't just use them for graphics, they use them now for actual numerical computations. And the reason why people want to use those is because there are, on a single graphics card, there might be 100 cores. Essentially, you can think of it as 100 processors itself. And so that really lends itself the ability then to do it for parallel processing. This topic and the previous thing that I was talking about will be more clear, I think, once we get to parallel processing. Do note that I have allowed students to look at this topic in my Tools for Statisticians class the last 2 years, and I had a student in each of those classes say that they were going to do that, and unfortunately they were unsuccessful. They couldn't figure it out. It is more of a tougher topic, but I think it can be very, very beneficial if we can figure it out. Note, for example, that there is actually a research group in the Department of Statistics at Duke University that focuses on how to use GPUs. There are packages in R that are set up to allow you to do it. You can also present something on mathematical software. So in terms of statistical research publications, R by far is the most prevalently used. The second is MATLAB. Okay. So you could talk about how to use MATLAB. It's the basics of how to get around in it. You could also talk about what are statistical capabilities. Maybe do some comparisons to R. There's some other mathematical software there as well. The key, though, with these mathematical software, if you're to present that, you need to make sure that all students can access it. In MATLAB, you would have to buy a license for it if you were to use it on your regular old computer. Now, the university does have a site license for it, so I don't know if it's free for students or not. If it's not, then that's a problem. But the supercomputers that we have on campus actually have MATLAB on it. While it will not be a nice, as you'll see once we get to this, talking about supercomputers, it will not be a nice little graphical user interface to use MATLAB. You can still submit programs.
If we're gonna do something like that, is it okay if it's on like these computers or the computers upstairs?
Well, students need to be able to do the homework assignment. Okay?
So we can't like, require them to have to
Purchase
stay
it.
at school and do that or something. I'm saying like these computers have MATLAB,
They do.
so I'm just wondering.
I think I would consider it. I hadn't thought of that possibility, but I would consider it.
Yeah, so on that note, when we're presenting a topic, should we present it both for users using like a Unix-based system and one's using Windows?
Well, by the time we do a presentation here, students will have the basics of how to use Linux on the supercomputers only.
Okay.
So if it's supercomputer based, sure.
Okay.
Otherwise, Windows based.
Okay.
Okay. So you just you have to take into account the student's background again for this kind of a presentation and what they will have easy access to.
Okay.
I don't want students to have to purchase, for example, MATLAB.
Yeah.
Speaking of Linux operating systems, so once we talk about high performance computing, that basically means we're going to use the supercomputers on campus. When we do that, I'm going to actually give about a half-day introduction to Linux, just enough so that you can get around on the supercomputers. You can, like, let's say, submit a program, an ARC program to run. So there's room for a lot more about Linux, and Linux is, I think you could easily say, in terms of scientific numerical calculations, is the most used over Windows. People who are doing, research use Linux. When I was a student at Kansas State, we had a nice Linux-based network of computers throughout our department, and so for grad school, for my first 4 years, I just only used Linux. And then I bought my own computer that was Windows-based, and I mostly did that, but I still ran all my simulations that I needed to do for my dissertation. I ran it all on a Linux-based system. So, it's good for you to get some background into Linux. And so you can kind of talk more about Linux beyond my high-performance computing section. But I think what also would be cool is that show how to, let's say, install Linux on your own computer or on a student's computer. And since you want to be careful, you don't want to screw up, obviously, a student's computer. You can actually install Linux simply on a USB drive. So you can show us how to install it, or on an SD card. And then show, well, what can we do with Linux? Well, there's R versions available for Linux. Let's look at R in Linux. The key is with the Linux, most versions are free. This is a little bit of a different topic. And you can talk about, I've heard it pronounced both ways, Kaggle and Kaggle. I don't like that latter form because that actually is a particular kind of exercise. So I'm just going to call it Kaggle. My wife laughed at me one time I first pronounced it this way, or the latter way. Anyway, look it up if you don't know what I'm talking about. So Kaggle is actually a company focused on data analysis competitions. Anybody ever heard of it before? Okay. So they host competitions simply from, let's say, a university class. But they also host competitions that a company actually will pay them to host it. And so, for example, and unfortunately my computer restarted before class and I forgot to pull this back up. So, for example, a new competition that was recently announced was one associated with the NCAA basketball tournament. So if you follow men's, I guess any kind of NCAA most any kind of NCAA sport, but especially for men's basketball, there are about 68 teams that participate in the tournament in this tournament every year to determine which team's best. And it's often a big thing for once the brackets come out in terms of like who's playing who, is to try to predict who's going to win the games. And so there is a recently announced data analysis competition that's trying to come up with some machine learning algorithms to predict it the best. So if you go to their website, you'll see what I mean. I guess as a side note, I think Warren Buffett's company, Berkshire Hathaway, I think they started last year. I think they're doing it this year, where they will actually give you $1 billion if you can predict all. There's going to be like about 68, 70 total games. If you can predict them all correctly, you'll get $1 billion. So enter it, and then I'll take my 10% fee for telling you about it. Okay. So you can present then. Well, tell us more about what Kaggle is. Tell us how we could set up our own competition. Tell us how you could participate in a competition. And again, they're using, and the reason why I think this is appropriate for our class is because computational statistical methods are used in these competitions. Again, it is kind of a different one than from the rest. Now, there are a lot of big data aspects of computational statistics, and we're not necessarily going to talk about them today, and it's not necessarily a standard topic in most computational statistics textbooks, but obviously big data is becoming bigger every day, so what you could do is talk about how can we handle big data in R, for example. R, one of the initial issues that people had with big data in R is that when you have a data frame, that's actually stored in the computer's memory. So if you have a huge data set, that's an issue. And fortunately, people have figured out ways to use R with big data so that that's no longer an issue. And so what you could do is talk about maybe some packages that discuss, well, how to handle big data. Sampling for Bayesian methods. So originally I was hoping to talk about Markov chain Monte Carlo methods in this class, but it's just we're not going to get to. And it's not necessarily a standard topic in computational statistics classes. So I don't necessarily feel bad about not getting to that kind of a topic, but you're starting to see it become more prevalent. As Bayesian data analysis methods are more integrated fully into the curriculum, rather than maybe as a separate Bayesian course itself at various departments of statistics. So what you could do is do a presentation on various MCMC methods, such as Metropolis-Hastings algorithm or Gibbs sampling. Here are some very introductory papers on it. The reason why I bring this up is because for my Advanced Inference 2 class when I was a grad student, I presented basically this paper during the whole class period. So with that, then you would need to show us, well, how can we implement? Well, tell us the basics of what Metropolis-Hastings does. How does it work? Why does it work? Show us how to implement it in a setting that everyone in class will understand, and that's a key. Other topics can be found from the books suggested for this course. So you can easily go through the Givens and Hoting book. That was a recommended book. You can present something on a genetic algorithm. That's a way to do optimization. You can present non-parametric density estimation, for example. And there's even some other bootstrap stuff in there. They have a little bit more. I mean, you could probably gain a lot more from taking a look at the Davison-Hinckley book that I suggested too. And if none of these ideas interest you, well, leave class. You shouldn't be here. But still, if you're looking for other ideas, take a look at the R Journal. Take a look at the Journal of Statistical Software. Take a look at r-bloggers.com. You could probably come up with some ideas in those locations. A key, again, is that you have to clear any topic you have to clear it with me. And don't wait till the last minute to do it. Also note that I may or may not have background in some of these topics. So just like when you do your dissertation, you kind of have to teach yourself off in some particular topic so you can do your dissertation. And again, your advisor may or may not have background in that area. So this is this is perhaps might be one of the first times in your grad school career here where you're kind of off on your own and you got to figure it out. So I think that's good practice for dissertation stuff eventually when you have to do that yourself. Okay, let me make sure that I discuss everything here. I think I have. Are there any questions?
As far as programming languages or software that's available to everyone, would it be okay if it's something that's available like on a free trial period for 30 days? Since we're not presenting until
I think that would be fine.
April,
That would be fine.
Okay, and then I have another question. As far as actually I lost it. Maybe I'll
Okay, that's fine. Any other questions? Yes.
So kind of back to my prior question. So I run Mac OS 10, but you want
You run, I'm sorry, what?
I have a Macintosh.
Okay.
So you want everything based on Windows?
Well, the key is it has to work on any computer that our students use, and still most students use Windows, so make sure it works on Windows.
Okay, gotcha.
Other questions? Okay. So let's get back to the notes. We were on page 95. So we were talking about permutation tests. And it's very closely related to the bootstrap hypothesis test. The main difference is how you take your samples. With permutation tests, you take it without replacement. And so I think the best way to even review the idea of what permutation tests are is just to jump into an example here. Let me get my red pen out. And so we're going to go back to this two-sample test for means once again that we saw with the bootstrap section. So we have two sets of data, y11 through y1n sub 1 and y21 through y2 sub n2. The key thing to look at is the sample size is n1 from group 1 and 2 from group 2. And we use the first subscript of these y's to indicate which group we're talking about. Now we can basically adapt approach number 2 that we saw in the bootstrap hypothesis testing to do a permutation test here. And if you remember what that was, basically what we did was we just kind of put all the data together into one overall group. And with the bootstrap what we did was we sample n1 observations from all the data with replacement. And then we sample n2 more observations from all the data with replacement. And the reason why that was essentially sampling under the null hypothesis is that basically what you're saying is that the data is actually coming from one overall population itself. And if it's the same population, of course, we have the same mean. And so if you also remember, there were some issues with that, and that is actually the hypotheses are stronger than just simply looking at the means. While you'll still get information about the means, yes, but truly the hypotheses are a little bit stronger. You're basically looking for a shift in I guess you could say the distributions. Okay. Now with respect to the permutation tests, what we do is we sample n1 observations from this whole group that we have, sample n1 observations without replacement. Then we sample n2 more observations without replacement. Or equivalently, since we sampled without replacement, once we got those n1 that we just sampled, we'll just take the remaining ones because that would be n2 more observations. So that's how you do your resampling under the null hypothesis of independence. Now, hopefully also you remember from last time that with the permutation tests, one of the big differences between that and the bootstrap is that we are essentially conditioning on a sufficient statistic. Our sufficient statistic is the order statistics, where we have put all of the data together essentially into one overall group. And so no matter how you do your sampling, no matter what you get for your sample, still when everything's combined, you have the same ordered statistics. So your order statistics do not change from one set of samples, or one set of resamples, I should say, to another. Now compare that to the bootstrap. When you're resampling with replacement, you might not get the same order statistics. In fact, you probably won't get the same order statistics for each resample. So that's what a permutation test does by taking samples like this. It's making sure that you have the same sufficient statistic for every single resample. Or maybe I should say same sufficient statistics rather than just statistic. Now, what do you calculate for every resample? Well, it seems to make sense intuitively to take simply the sample difference of sample means. You could also take like the studentized quantity that we saw before too, with the bootstrap. Well, how many total resamples are there? You could also call these permutations too. So where the name permutation comes from is essentially all we're doing is mixing up the data a little bit. So we're permuting it. So that's why it's called a permutation test. So we could call our resamples permutations if you wanted to. And just going back to your days when you first learned about combinations, it's just simply n1 plus n2 divided by n1 plus n2 choose n1 is the number of possible permutations. Now with respect to the bootstrap, we would be in this situation 2 times n1 plus n2 minus 1 choose n1 plus n2 minus 1 distinct resamples. So you can see, or if you can't see, just plug in some numbers in there, you'll see that with the bootstrap you will have more unique resamples than you would with a permutation test. Now was there a question?
I was just wondering, like, unique resamples for bootstrap, like, since we do it with replacement.
Unique. So a unique resample. So that's what was actually in the notes, which is a little bit different than what was in the assignment.
Right.
Okay.
And that's why we have that combination.
And there are
Like the ones for bootstrap, because it's unique. We have that 2 times n1 plus n2 minus 1.
Yeah. So with these different possible permutations, then each one is equally likely. So if each one is equally likely, well, you should think of it. Why is it equally likely? Just think about what we're doing here. We're essentially mixing up the data, and every mixing up the data you would think is equally likely to occur if the null hypothesis was true. Whether or not one observation is from, let's say, group 1 or group 2, under the null hypothesis, well, it could be 1 or 2. And so that's why everything is equally likely. So every single permutation has a probability of 1 over W. And so if you know that, then you have a way to come up with essentially with this distribution for T star. It's a discrete distribution. Now, even though with a permutation test you have less resamples than you did with the bootstrap, still, this could be a large number. And so what do? You randomly select permutations typically, like 4,899, like what we've done with the bootstrap. Okay, so here's a very simple example. There's actually no program with it because it's just so simple. This comes right out of Jim Higgins's non-parametrics book. And he simply had the following example. Let's say that 7 new employees of a company are being trained to do their job with 1 or 2 different methods. Once they're trained, they're given a test. And so for 4 of the new employees, they're assigned to the new method of instruction, so that treatment group. And the first person got a 37 on the test, the next person got a 49, and so on. Then using the traditional method, 3 people were assigned to that treatment group. 23 got, I'm sorry, the first person got a 23, the next person got a 31, and so on. And so, you know, a common question that you might want to be interested in answering is, well, do the mean scores differ between the 2 different training methods? You know, probably your hope is that the new method improves your grade on the test on average. So in this particular case, then, there are 7 choose 4, or just simply 35 different possible permutations. So one possible permutation of the data would simply look like this. Y11 star is 46. And notice where that 46 came from? It actually came from group 2. Y12 star is 49. Where did that one come from? Well, it just so happened to come from group 1. So all I'm doing is just simply mixing up the data and then assigning them to particular treatment groups. This possible permutation under the null hypothesis has exactly the same probability of occurring, 1 over 35, as this one. And notice what that one is? It's just the original data. Again, notice how the order statistics here do not change. Again, if you look at the combination of the 2 groups, the order statistics are not changing. So essentially, you have the same EDF for the combined set of samples. Okay, so here is then from Higgins's book, the listing out of all possible permutations, all possible resamples. Number 2 is what was actually observed. So if you take the sample means for the 2 groups, subtract them, you get 16.2. So on average, at least for this sample, group 1 had a higher score on average by the amount of 16.2. And so what we want to do, and just what we do in any kind of hypothesis test, is we want to know, is this unusual to be this high, to have this big of a difference if the null hypothesis was true? And so by looking then at all possible resamples, all possible permutations, we can make a judgment of, well, would this be unusual? And so, for example, the most extreme case results in this as a permutation or resample, and you get a difference in means of 21.4. The next most extreme case is negative 19.4. The next most extreme case, the third most extreme, is 17.7. And look at this. The fourth most extreme case is 16.2. So fourth most out of 35. And so we need to make a judgment then based upon that is what we observed unusual if the null hypothesis was true. We relate it back to this probability distribution here. So if I want to compute then a p-value for testing differences of means, I basically use that same idea. 4 out of 35 is my p-value, because it's the fourth most extreme, which is 0.1143. So in some sense, it's kind of marginally significant, kind of. But you know, for some people, obviously, it might not necessarily be enough evidence to say, yes, indeed, this is unusual, that there is actually a difference in the means. So that's how you calculate a p-value. Very simple. Hopefully it's very intuitive. You know, some of these intuitive ideas can be used like in the Stat 218 kind of course. I think students maybe sometimes would have maybe a better idea of grasping it. You know, you don't have to talk about the sufficient statistics part. You'll scare them away if you do that. Well, how else can we calculate the p-value here? Well, with a two-tailed test, we can essentially use the same expression that we did before for p-value with the bootstrap. And if we do that, we get 0.1667. I, Lisa, prefer this first approach because I'm actually able to see the entire distribution myself. The second approach here, is nice when, let's say, you have to actually take your resamples because there's just so many different possible permutations of the data that can be done. But you can see, they're still in the same ballpark as you would expect. Some people will actually use this then as a p-value too. And I briefly had showed that before when we were talking about bootstrap p-values, where now you're looking at the absolute value of t star greater than or equal to the absolute value of t. And essentially, that's kind of like what I was doing here. So that 4 corresponds to that. You get 0.1389. Now, just please be careful here when you use this kind of a way to calculate a p-value. You have to basically hope that your distribution itself is essentially symmetric about 0. Because if it's not symmetric about 0, you could have some issues. Just on your own, think of a special case where, let's say, all the t-stars had to be positive, for whatever statistic that you're calculating. And suppose you get a t-star that's very, very small. Your p-value is not going to be small. Just try it on your own, and you'll see that, why this can be an issue. Okay, well, what about a one-sided test? And in fact, probably in this particular case, you would probably prefer a one-sided test because you would think that probably this new method is going to be at least as good as the traditional method. And so you want to know, well, does a new method give you some improvement? So in that particular case then, there was only one other possible resample that was actually more extreme, that 21.6. So my p-value could be 2 divided by 35, or 0.0571. Again, marginal evidence suggesting that yes, indeed, there is some treatment effect, you could say. Using the method that we had with the bootstrap, you get 0.0833. Also, one reason why I like to present these different ways to calculate p-values there is not necessarily to confuse you, but people will use different methods. And so, especially if you're, let's say, looking at, maybe you come across a new function in R and it does something like this. And to validate it, maybe you might try to do the tests on your own. And you notice that your p-value might be different than what this function gives you. Well, it could be simply because of how they do their p-value calculation, not for any other reason like programming error. Now let's compare this to how we would do this test normally with just a simple t-test. So I use the t.test function, and I have var.equal to true here, because essentially this test that we just did here actually assumes equal variances. Because remember, just like even with the bootstrap, we are looking for shifts in the distribution. And since we are essentially saying that they have the same distribution except for that shift, well, it means that they have the same variance. Because, of course, a shift in a distribution is not going to change the variance. And so the t-test gives us a p-value of 0.09, very similar. And so this also, if you've seen that YouTube video corresponding to assignment number 3, again, you should be asking yourself, okay, which is more intuitive, let's say, for people who are just coming into the statistics, understanding how this works and why it really does work versus doing this permutation test. If we did unequal variances, we get a p-value of 0.12. You could do one-sided tests as well. You could specify alternative equal greater in the t.test function. You get similar p-values to what we did before. Okay, so that takes us to page 101. Okay, I think we've already essentially covered the first 2 bullets there. The third bullet, more robust versions of the test statistic can be used. How about trim means? You could do it. Nothing wrong with doing it. Maybe even medians. Maybe you're interested more in that kind of measure of central location. You can do that. Just very simple. Just use medians instead of means. And that's one reason why, people like this. Because means aren't everything. So here's the question. Suppose you want to do a one sample test for mean. So notice there is a little bit of error in the notes. You're testing mu is equal to mu 0 versus mu does not equal mu 0. What I had in the notes was nonsense. For some constant mu, 0. How would you do this with a permutation test? Hopefully you didn't print off my comment. Don't look at my comment if you did. How would you do this if you were to do a permutation test? Well, what happens if you permute your data? Your sample itself. You're going to get the same thing over and over and over again. So you might be thinking, well, why don't we just adjust the data like we did with the bootstrap? Do your order statistics change? Yeah, because you have adjusted data. So you cannot do a permutation test for this simple test of the mean. And then this also then is a good illustration of, well, there are limitations with the permutation tests. Also, just figuring out exactly how to do your resampling, just like with the bootstrap, is you could say maybe it's somewhat of a limitation too, because it's very problem dependent. I guess one other side note that's not actually in our lecture notes is that I actually so when I first saw this kind of stuff when I was in grad school, it really interested me. So Jim Higgins allowed myself and 2 other students basically take a readings course on the history of permutation tests. And it's very interesting. A lot of these ideas were originating, for example, we looked at some papers from the 1930s. And even I think maybe 1930s. It's very interesting that people had these ideas back then to do that. But it's only over the last 20 years that we essentially have had the computing power to make them viable in most situations. And so what would have been interesting in terms of the direction that statistics would have gone if back then in the 1930s, if we would have had the power to do this kind of stuff. Would we be so focused on using a t-distribution approximation nowadays if we had the computing power to do this kind of stuff when it was introduced? Also, you should think about, well, maybe where is statistics going? Statistics is becoming more and more and more computer-based. More and more, basically using a computer to simulate a probability distribution. If you've had any Bayesian stuff, for example, simulating a posterior distribution is done all the time. Why is Bayesian becoming so popular? It's because we didn't have the computational power until the early mid-1990s to do this on a regular basis. Okay, so let's take a look at another permutation test. Now this is with the Larry Bird example. Well, you have to think about now, what would be the sufficient statistics in this particular case? Well, in a contingency table situation, so here's my contingency table, drawn kind of oddly here. It's a 2x2 table. We have X, we have Y, we have 2 levels, 1 and 2. Now, if the null hypothesis was true, and I want to know, well, what would I expect the cell count to be? What would I do? I simply look at the corresponding marginal counts to figure that out. So the sufficient statistics that are kept constant for every single resample are simply the row and the column margins. Because that's all the information you would need to figure out what each of those cell counts were if independence was truly true. Truly true. Okay, so how do we take our resamples then? Well, we do it as follows. Put the data again into the raw format. So in other words, every observation is simply like a row in your data frame. So like with the Larry Bird data, we had 338 rows. And we had 2 columns of data, One that said, okay, what happened on the first attempt? The other one said, well, what happened on the second attempt? Made or missed. Okay? And what we're going to do, in order to make sure that we keep the row and column margins fixed, in order to take our resample under the null hypothesis, is just simply this. Resample from the row, the first free throw responses, which was the row response. Resample from those with replacement. Also, I'm sorry, without replacement. Then also with the second free throw attempt, resample without replacement as well. Once you get those two vectors that are resampled, you simply put the two vectors together, and there's your whole data set for resample. Very similar to what we did with the bootstrap. The key point is that since we were sampling without replacement, all we're doing is simply mixing up those made and misses. And the margin totals will be exactly the same as they were originally. Now there's actually a little bit of a simplification here. You only need to do this randomly permuting these responses only for either the second free throw or the first free throw. In other words, just for the columns or just for the rows. Because again, you're not changing the margins at all. All you're trying to do is come up with some kind of random combination of the made and the misses for the first free throw and the second free throw. So it doesn't matter if you decide to permute them both or only permute one of them. You still get a permutation of the data as a probability of 1 over W. Okay. So now for every resample, calculate x squares, star, let's say. Repeat this whole process capital R times, and then calculate your p-value in basically the same way as we did before. I guess I've answered the questions for you. Are there any questions about my answers to the questions? Okay. So let's look at how we can do this in R. Make this bigger. As I said, unfortunately, my computer decided to restart before class, and I don't know why it did that. And so normally I would have all this stuff ready to go. And unfortunately, I do not. Let me just get everything into the correct format. So our raw format is set 2. There's the raw format. And I need to make sure that I tell R I'm going to use the boot package. And eventually I get to the permutation test approach. So just like what we've done before, let's first talk about the boot function, how to use it. So set 2 contains my raw data, and all I'm going to do is simply permute the columns, the column responses, or in other words, the second free throw attempt results. And so notice here I simply have set 2, and I'm taking then that second column of my data frame. My statistic is going to be calculated in a function called x.sq. R resamples, and here's the big difference essentially from what we've done before. For sim equal, we've always put ordinary in the past. Now we're going to say permutation. And then also I'm going to take advantage of the ... format for the boot function. And I'm going to pass into my x.sq function my row variable. So I have an argument called row.var, and that's the first column of set 2. If I take a look at x.sq, you see the usual format. Data, my I indices that the boot function comes up with, and then also this extra component row.var. Inside here, I pick off my column variable, just like what we've done in the past, but now this is essentially my resampled version, my permuted version. And then I use the chi.sq.test function as we've done in the past to do this kind of to get x squared. Notice I immediately return the statistic portion of it only. So of course I can try it out with my original observed data, and I get the same thing as I've done before. And so then if I run this in R, it cannot find R. There's so many things called R here. And we'll also calculate the p-value too. The computer runs for a little bit, and eventually, it shouldn't take this long. There we go. You know, we get the usual kind of output that we've got in the past. I calculate my p-value as 0.65, which is very similar to what we got with the bootstrap, and also what we got with using a chi-square approximation. Okay, let me go back to my notes here. Oops. Okay, so remember my summarize function that we saw before that would draw some plots and help you, gives you a visual picture of, well, is a chi-square 1 approximation truly appropriate? Well, I apply that same function now here to my t-stars that I got from my permutation statistic, or x-square stars, I should say. And this is what I get. And once again, we can see that a chi-square approximation works fairly well. But something else that you also see is this here. Look at the QQ plot. Notice we have a whole bunch of points that are kind of in a vertical line there. What is that representing then? Or why does that happen? It's the discreteness of this x-square star. Remember how there's a lot less possible permutations than there are with the bootstrap. With the bootstrap, we didn't see this. But now, here with the permutation test, we see more of the discreteness that occurs. And so, you know, while the chi-square 1 approximation is, you know, it's doing the best that it can, essentially, you know, given what we see there. It's definitely not perfect. Obviously, x squared has a discrete distribution to it. Okay. You could also, you know, if you don't believe me that indeed that you do have these row and column margins exactly the same for every resample, similar to what we did with the bootstrap, we could simply pull out the indices, let's say for the third resample here, and take a look at the actual contingency table. So I use the boot.array functions we've done many times before. I actually then get my, this is one resample contingency table. Here is x square star, let's call it 3. This is for the third resample. And you can look at the column and row totals for what we just got for this third resample, and they are exactly the same as what we observed originally. Okay, just to show you the discreteness of this x square star distribution, I took all my x square stars. So these are all my x square stars. I rounded them to 2 decimal places, and then I used the table function so that you can see that indeed there is just really a finite number of possible values of x square star. Now there's actually an easier way to do this test, not through using the boot package, and that's because chi-sq.test actually has an argument that allows you to do this test. Because you know, people put together R realize a lot of people want to do this kind of a test rather than rely on a chi-square approximation. So in the chi-sq.test function, there is an argument called simulate.p.value. If you say true, and then our version of the letter R is what they call B. If you say 4,999, chi-sq.test does the resampling for you and gives you a p-value, which matches what we had before. So here's a question for you. How can we perform this test with the likelihood ratio test statistic? So the -2 log lambda. You know, often that's used to test for independence as well. What would we need to change with what we just did here? Perhaps the answer is too easy. What will we need to change? Instead of using an x.sq function, you write a new function that calculates -2 log lambda. That's it. So similar to what I mentioned before with when we were testing for the difference of means, I say you can use trim means, you could use medians. Oh, why don't you use negative 2 log lambda instead? You could do that. Just replace the statistic with something else. Now, doing this test here, this permutation test, is very, very closely related to Fisher's exact test. So if you've ever seen that before, look at the similarities between it, or buy my book and look at section 6.2. How could you find the permutation distribution with all possible permutations? Well, just simply iterate them all out. The key is this, and this gets into what Fisher's exact test does, actually. So let me find the original contingency table. Actually, when I just do this, wasn't smart. C.table. There we go. So there's the original contingency table. So if I fix the row totals and column totals for that table there, how many of those 4 cells would I need to know before knowing the entire table? 3. Not 3. Lower. We'll play the Price is Right game. Lower. Lower.
1.
Ding, 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 ding. Yes, that's all you would need. Because think of it this way. If I know this total here, if I get this number, I know what that was. And same thing happens there. And so what Fisher's exact test does is that essentially that cell where you see the 251, if you think of that as a random variable, it actually has a hypergeometric distribution to it. And so a lot of the probabilities that we just found could be equivalently found with a hypergeometric distribution, and that's what Fisher's exact test does. Okay, now I lost my place here. I'm going to go through the rest of this quickly because we only have a few minutes, but essentially we're just doing the same thing, but now for a different contingency table. Actually, so this is that table at table 2.10 of Agresti. If you remember, there was a whole bunch of zeros in that table, and the bootstrap failed. So how about we just apply essentially the same code that we had before for that 3x9 table. Now just apply it as before. If you remember, when we use a chi-square approximation, we get 0.1342 as a p-value. But that was somewhat in question because, well, we had those low cell counts. So when I do the permutation test, look what I get for my p-value, 0.0014. Wow, that's a big difference. And that's saying that what I observed from my original data is very extreme. I would reject HO here. Where before, with 0.1342, you probably say, no, don't reject HO. There wasn't sufficient evidence. But this permutation test gave you the power to see that indeed you do have dependence. Why is that? Well, it's because the chi-square distribution here, which is chi-square 16, is a very poor approximation to the true distribution of x squared. You can see it in these plots here. So, I mean, it's just extremely poor. And so you can see a case where essentially asymptotics, using an asymptotic approximation, fails. So it's not just the bootstrap failed, the regular old chi-square distribution approximation failed, and permutation test works. Okay, so we are out of time. Are there any questions?
I have a question about the presentation. Are we able to write on that monitor?
No.
Okay, so we should prepare and present just like, so we're just gonna talk and not write.
You could buy a tablet where you could write on it and bring it in. In fact, I do encourage students to use their own computers in here. And the reason being is because I want to record everything, and there's not a microphone with this. And I can't, I don't have a good way of putting a microphone with this because this is not under statistics control, it's under SNR's control. So I would encourage you to use your own laptop.
So does your camera just hook up to our computer then?
Well, what we would probably do is not use a camera and just simply get your voice and also what's on your screen. That's easier. I mean, we could do the camera, but then you're going to install drivers and most students don't want to have to hassle with that on their own personal
Or
laptop.
we'd be able to see what's on our screen.
Yes, yes. So the only thing is you won't see the live action video of yourself. Take a look at some of the examples,
Yeah.
and you'll see what kind of recordings that
Yeah,
Okay, that's it for today.
Mhm.